Now, for this one, we get x equals y cubed and x equals y squared. So we can't use that top minus bottom if we want to keep these functions as they're written right now. What we can do alternatively is picture that idea of top minus bottom and then rotate it. So rather than doing top minus bottom, we'll do right minus left and find our derivative with respect to y instead. So our rightmost function, is that y squared. And then our leftmost function is that y cubed. And then we're going to find the antiderivative with respect to y instead of x. And then we care about the two y values where those two meet. So the first time that they meet is down here at 0. So they meet at 0. And then they meet up here at 1, 1. But we do want this y value of 1. So we can just anti-differentiate both of those things. So we get y cubed over 3 minus y to the fourth over 4, going from 0 to 1. Now we just need to plug in our top value minus our bottom value. So our top value for this 1, so that's going to be 1/3 minus 1/4. And then our bottom value is going to be minus 0 over 3 minus, well, cubed, but whatever. 0 to the fourth over 4. Oh, that's just 0. So later. So we need to do 1/3 minus 1/4. So that is 4/12 minus 3/12. So our answer is 1/12. So that is the area between those two curves. Now, if you don't like this idea of anti-differentiating with respect to y, it does also work if we find the antiderivative with respect to x. What we would need to do is we would need to solve those equations for y. So we can get the cubed root of x here and the square root of x. And then we would set up our top minus bottom. So our top one is the cubic function, and our bottom one is the square root. And then when we anti-differentiate, we get a much uglier anti-differentiation. We still have 1 and 0 because it happens to be that they meet at 0, 0 and 1, 1. Otherwise, these would have to change to be the x values. But once we do that top minus bottom, we still get 1/12. So we get the same answer both ways. If we integrate with respect to x and do top minus bottom, or if we integrate with respect to y and do right minus left. In this example, I would like to show you a little bit of a shortcut. So we do want to do our proper integration for those two curves. So do top minus bottom. So our top curve is going to be the red curve, which is 2x squared, minus our bottom curve, which is the blue curve. So minus x to the fourth minus 2x squared. Parentheses. Ew, that parentheses is pretty gross. Dx, and then we are integrating this thing. Now here's where I want to get a little sneaky. If you look at these two curves, you might notice that this curve is identical to that one. So they are symmetrical about the y-axis. So we could integrate from -2, because that's where one place that they meet. And then the final place they meet is over here. So we could integrate from -2 to 2. But you know what? Then I'm going to have to plug in the -2 and the 2. And it's really easy when we can plug in 0. So here's my idea. Rather than doing that whole area twice, we could just integrate from 0 to 2, just finding this piece on the right-hand side, and then just double it to make our integration a little bit easier. Since they are symmetrical, we are able to do that. If they weren't symmetrical, then we couldn't do this trick. But since they are symmetrical, let's just save ourselves a little bit of trouble and just double it. I am going to clean up that integral before I actually integrate, because I bet I could combine some of those things. So this is the integral from 0 to 2. This 2x minus -2x squared. That is 4x squared minus x to the fourth dx. Now I'm all set to integrate, so we get 2 times 4x cubed over 3 minus x to the fifth over 3. Why am I writing 3? 5. Going from 0 to 2. So now when we're plugging stuff in, all we need to plug in is that top value, because when we plug in that value of 0, we get 4 times 0 cubed, that's 0, and then the other one's also 0, so we just need to do the top value. Huh, how neat. So that's going to be 4 times 8 over 3 minus x 2 to the fifth is 32 fifths. So that is 32 thirds minus 32 fifths multiplied by 2. Now, if only there were something like common numerators, and then we could just combine those two things, right? Ah, oh, dang it. So let's see. I'm going to get a common denominator of 15. Well, you don't need to join me for all of that. Let me just figure this out. So I got 160 fifteenths and 96 fifteenths, and then subtracted them, got 64 fifteenths, multiplied by 2. 128 fifteenths is the area between those two curves. All set. A lot easier to do it that way than trying to do that twice. Ugh. So what we talked about in this video is finding the area between two curves is as simple as finding the integral from the top minus the bottom, similar to what you would do in the fundamental theorem of calculus, but now you're subtracting two functions rather than evaluating at those two different values. Now, if your functions are solved with respect to y, you can still just integrate from that. You just do right minus left for your integration. And that's it. Thanks for watching. Bye-bye.